Hey guys, how's it going? In this video we're going to go over 3 worked examples to show you how to do problems involving electromagnetic radiation. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you'll be able to apply what you learned in that video to this one. So let's get started. Question 1 says that electromagnetic waves in a vacuum are said to be transverse. Explain the meaning of transverse in this context. Well, this is a bit of a reminder from National 5 physics, where there are 2 types of waves, known as longitudinal waves and transverse waves. And a transverse wave is one in which the particles move perpendicular to the direction of travel of the wave. In the advanced higher waves topic, you see an example of transverse waves, which are stationary or standing waves. And transverse waves look like this, where you've got the particles moving up and down, which is perpendicular to the direction of wave propagation or wave motion, which is moving side to side. Question 2 says to list all the types of the electromagnetic radiation in order of decreasing wavelength. Again, this is a bit of a reminder from National 5 physics of all the different types of electromagnetic radiation and their order in the EM spectrum. So we start with radio waves, we then have TV waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And this is going from high wavelength at the radio waves, which is also low frequency, all the way down and decreasing in wavelength to the smallest wavelengths of gamma rays. And these are the highest frequency waves. So this is decreasing wavelength going down this way, which is the same as increasing frequency. Lastly, question 3 says that the speed of light in a vacuum c can be written in terms of 2 constants. C equals 1 over the square root of epsilon naught mu naught. Part A then says to show that the speed of light in a vacuum is 3 times 10 to the 8 meters per second. So we can use this equation to do that. So writing down what we know from the question, we're trying to find c, the speed of light. We know that epsilon naught from the datasheet is 8.5 times 10 to the minus 12 farads per meter, and this is also known as the permittivity of free space. We then have mu naught, which is another constant from the datasheet, which is 4 pi times 10 to the minus 7 henries per meter, and this is known as the permeability of free space. We can then write down our equation, so we have c equals 1 over the square root of epsilon naught mu naught. Substituting in our numbers gives 1 over the square root of 8.85 times 10 to the minus 12 times 4 pi times 10 to the minus 7. Putting that into your calculator now, it gives you a final answer of 3 times 10 to the 8 meters per second. Lastly, part B says to show that c has the units of meters per second. So we want to simply show that the speed of light c has the familiar units of meters per second. So in order to do these questions where we try to prove the units of a variable, we need to consider the units of the different quantities that make up that value c. So epsilon naught is in the equation for c, and so is mu naught. So epsilon naught we said has units of farads per meter, whereas mu naught has units of henries per meter. And we can use these two to try and arrive at this expression of meters per second. So first of all, since c equals q over v for capacitance, we can say that 1 farad is the same as 1 coulomb per volt. And that's because charge is measured in coulombs and voltage is measured in volts. So we can also say that since back EMF E is equal to minus L di by dt, then if we rearrange for inductance L, this is equal to minus epsilon over di by dt, the rate of change of the current. And this means we can say that 1 Henry for inductance is equal to 1 volt over amps per second, which equals 1 volt seconds over amps. And that's because of this inverse seconds, seconds to the minus 1, on the denominator, which we can rewrite as seconds to the power of 1, which is on the top as the numerator. We can also say that since I equals q over t from the definition of current, the charge transferred each second, we have 1 amp is equal to 1 coulomb per second. And this means we can replace the amp here with coulombs per second. So what we then need to do is multiply the units of epsilon naught and mu naught and then take the square root of them, because that is how we find what c is. We're also then going to take 1 over that square root. So multiplying the units together, farads per meter times henries per meter gives us coulombs per volt meter to the minus 1, times volt seconds over amps times meters to the minus 1. But remember we said that ampere can be replaced with 1 coulomb per second, so I have coulombs per volt m to the minus 1 times volt seconds squared over coulombs per meter. And that's because we've replaced this A with coulombs over seconds, but because we'll have the volt seconds over coulombs over seconds, that seconds can be brought up to the top and multiplied by whatever's on the top. So we get volt seconds squared over coulombs. And as I said, that's since 1 amp equals 1 coulomb per second. So what we can then do is simplify this, cancelling the c and v terms on the top and bottom, you'll see we end up with m to the minus 1 times second squared m to the minus 1. And simplifying this further, we have m to the minus 2 seconds squared. But remember we said we need to take the square root of this, so we can do the square root of m to the minus 2 seconds squared is equal to m to the minus 1 s. And since our equation for c is 1 over the square root of epsilon naught mu naught, then we need to take 1 over this, so we get 1 over m to the minus 1 seconds is equal to meters per second. So we have proved that the units of c is meters per second by manipulating some other expressions. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.